I know everyone's probably burned out from listening to so many talks, so I'll try to keep it interesting for you guys. My project was searching for brown dwarfs in the Orion molecular cloud. My advisor is Dr. Tom McGath, and I'm from here at the University of Toledo. My name is Heidi. Alright, so it's important at first to understand what brown dwarfs are and how they form in order to grasp the project. So brown dwarfs are often called failed stars because they're between the mass of, they're often called failed stars because they're unable to achieve nuclear fusion. So they can't fuse hydrogen to produce energy, so they just slowly cool off and die. And these objects are between the masses of small planet, or of large Jupiter-like objects, or large planets, and small stars. So they would be out past the M stars in this chart. And right here at the University of Toledo, a few months ago, a group found a brown dwarf that was approximately 50 million years old, which was a fairly important discovery because it was a very small brown dwarf, which is a free-floating small brown dwarf, which is rare. And I'm trying to find ones that are like that, but still have the materials in which they were formed still surrounding them. The 50 million year old one was all the gas and dust that formed it had already dissipated. So I'm looking for ones that are about 1 million years old that are still in their star forming regions. Now, brown dwarfs can form in one of two ways. Like a star, which this right here is a protostar, and you can't really see much in this, but this is what it would look like if we could just cut away part of it and look inside. So stars form in areas, or molecular clouds, where the gas in dust is disturbed in some way, and it starts to collapse on itself and form a star. And it will be spinning quite fast and form disks around it, which will go to about the equator and then keep supplying the star with more gas and dust to help it form and grow larger. And some of the material will be ejected into these outflows. Sorry. But for a brown dwarf, it's harder for it to form in this way because the gravity and the pressure will fight against each other, and there won't be enough gravity to form it, to condense it, and it won't have the proper density to stay together. Unless there are some regions where the gas is more dense and can form brown dwarfs of small sizes that form this way. But the other way is in the disks around the stars. If the gas from when the star formed in this disk condenses in the same way, but kind of like a planet would, but in the same way that the star does, then we would have a brown dwarf, and it would form as a binary companion to the larger star. Now this is Orion, the constellation Orion the Hunter, and the Orion molecular cloud. And this is my hunting ground, if you will. So research has actually been done by Kevin Luman in 2012 in the more densely populated areas, so the areas that have many more stars, like around in here, and they've found how many brown dwarfs there are in that region. But in order to fully understand how they form and in what way is the most prevalent and that kind of thing, we have to look in the lower density populations, like right around here, which is where I'm doing my work. Now, all the images that I'm using have been taken with the Discovery Channel telescope, or the ones that I'm working with right now. I will be using other ones. But the ones I'm working with currently have been taken with the Discovery Channel telescope in these two bands. And these are actually very red bands, but they're still in visible light. So these are some of the images I've taken. So a mosaic is when you take all of the images of a certain field and just stack them on top of each other to get the best signal to noise and get rid of any contamination from stray cosmic rays that may have hit the detector or other contamination. So this is one of the fields that I've been working with a lot, and you can see some very cool features. This is a protostar, and you can see some of the dark cloud over here, which is where the stars form in denser clouds. But all of that cool stuff in this pretty picture is not what I'm looking at. Unfortunately, I'm looking for all the tiny little things like these right here, which are kind of barely visible. And I'll be trying to find them in the farther infrared, where they're a lot more visible. But in order to do this, I first have to calibrate the data. So with the data we took, you can get it to a certain, you can get it to fairly good accuracy, but in order to get it to be nearly perfect, we have to compare it to stars that we already know. So this is an image taken with the DCT, and you can notice that these stars are the same as these. These are called standard stars. They would be like a control in an experiment. You can compare them and make sure that your data is accurate. So we can find how far off the data taken with the DCT is from the magnitudes and the brightness of these stars, and fix it so that we can make sure our data is proper and we can get the proper magnitudes of all of the stars and brown dwarfs to make sure we're not getting background stars or other things. So to do this, I use a program called Popeis, and this is just an example of field that shows all the stars. Sorry. It identifies all the stars, and you can find out the brightness, the magnitude, and a whole host of other information, which will then go through each star and compile a list of what their brightnesses are and compare them to other fields in the different bands. So the two bands I have, along with infrared bands that I will be adding soon. So this is a color magnitude diagram of the two bands that are the two colors that I have, and to show them brightnesses and magnitude. So right down here would probably be the most likely candidates for what I'm looking for in brown dwarfs that might be, well, things that could be brown dwarfs or might just be background stars trying to fool us. So in order to find out if they truly are brown dwarfs, I'll have to take spectra of them, which I'm hoping to get time on nights, which is part of an instrument on the DCT, to get spectra of these brown dwarfs. This is an example spectra that was taken at Mauna Kea. And right here and here are water absorption lines in both our atmosphere and the stellar atmosphere. And based on how wide those lines are and how much water there is, it actually helps to determine this point here, which tells us how hot the stars are, and then from that we can determine how big the stars are and how massive. And that will tell us whether or not they are brown dwarfs. So what's next? I will be making a list of all of the stars in the two bands that I have, along with in J and K bands, which are farther infrared bands. They are infrared bands, sorry. And with those, I will be compiling an entire list and then finding all the stars that could be brown dwarfs, and then eventually getting the spectra of those to determine whether or not they are actually brown dwarfs. And with this, I can help to determine how the brown dwarfs are primarily formed. And this is in the I band and the K band, the same image. So you can see a lot more stars in the K band, which those are a lot fainter and they'll show up more in the heat than everything else.
What's the advantage of going so far into these, or towards the optical for looking for these brown dwarfs? I'm just confused why we're doing that and not getting infrared images that are deep in the J or K.
We have those, we're just trying to find things that are visible in the optical that are much brighter in the infrared, so we can just see the whole spectrum.
But wouldn't you be more likely to find a brown dwarf if it's invisible in the optical in the LMI and only visible in the infrared? Or am I wrong?
I'm not entirely sure. I mean, you can find them whether they're visible or not. It just depends on, the visible ones are more likely to be younger because they're still showing, still fairly bright, but the ones that are in farther infrared are cooling off, so they're dimmer to optical. So I mean, you could find them either way.
Yeah, you can use it gives you just more color information,
Okay.
you know, to get it through the infrared. Depending on, so it helps you just look for the coldest objects. Yeah.
A related question then, if you actually have 4 band passes, is that enough to give you enough information on whether it's a brown dwarf, or do you really have to go to the spectrum?
Well, we would have to go to the spectrum. We're just trying to find, with this we can only determine stars that are very dim in optical and then get brighter as farther infrared we go. But we could also be stars that are moving away from us and are redshifted, that are background stars, or stars that are also extinct, with a lot of extinction. So we have to get a spectra to determine if they're actually brown dwarfs.
If you go to the slide number 7, it's, on the G band, I saw somehow there's kind of interference patterns. Does it?
Yeah, that's called fringing, and it's actually caused by the way that the light goes into the detector. It has interference, and when it kind of bounces in the detector and causes interference, and that causes interference waves.
Yeah, then does it affect your conclusion?
It doesn't really affect it. I mean, I could take it out. I could possibly take it out if I wanted, but it doesn't really affect it. So. Anyone?
Yeah. I just have a very naive question. So you showed, at one point you showed a map of the sky and you showed a reference map. No, like it was two plots on the same slide. Landmark, that's it, yeah. And I just noticed that there were more stars in one. I noticed there were more stars in the landmark than in the one, right? So I just wondered why.
I'm not entirely sure what band this is. It might just be in a band where
Yeah.
it can detect a lot more, but it's just to show those stars aren't both.
All right, let's thank Heidi.